So from last time, we saw these for each irreducible representation, you can associate it with a character function, and they form an orthonormal basis for some subspace of your L2 of G. So in this video, we're going to clarify what is this span of these characteristic functions. So let's just first observe one thing about these characteristic functions. So if I have two things, let's say G and H, this is just no other than the trace of the pi G times pi H. But being a trace, the good thing about trace is that trace of AB and trace of BA, they are the same. So if you just consider what's the trace of AB, that's just equals to the trace of BA. That's just basic linear algebra. You can just write AB as a matrix, and you compute the trace. And so this one, you can swap the place with pi h and pi g, so it becomes the trace of pi h and pi g. And this is just no other than the trace of pi of hg, so which is the characteristic at hg. Okay, so the same chi-pi evaluate at hg. So you see your function really satisfies this additional condition. The chi-pi evaluate on gh is the same as evaluate on hg. Okay, so these kind of function has some special names. So let's give them a definition. So I say a function f is called central. F is defined on this group. If it happens, I have the f of xy is equals to f of yx for all the xy inside your group. All right, and equivalently, this can be also be defined this way. So equivalently, this is just means f of yx y inverse is equals to f of x. Okay, so basically, these f will have the same value on each of these conjugacy class. Okay, so whenever you conjugate your x by y, the f value doesn't really change. Okay, so that's what they mean by central. So essentially, we saw that each of these chi-pi are going to be central, a central function. So let's just define some notation. Let's use the ZLP of G to be basically all the f inside the LP of G, where f is central. And also you can do the same thing for the set of continuous functions at ZC of G to be all the f inside C of G, where f is central. Okay, so and if you recall from the group theory, the reason I use this letter G is in group theory, you usually use the Z to represent the center of a group. Okay, so your LP space, we're going to see there, in fact, a Banach algebra structure, and so it has a multiplication structure. So the center essentially just means it commutes with everything else. Okay, so that's basically justifies why I use this letter Z. So here's the proposition. So I have the Z of LP of G is going to be the center, and also the ZC of G. Okay, they are the center of the Banach algebra LP of G. Okay, this is as a Banach algebra. So basically it means, so it's a Banach algebra. So essentially it just means Z of LP of G basically contains all the f inside the LP of G so that it commutes with everything else. So f convolute with G is equal to G convolute with f for all G inside the LP of G. Well, first of all, I need to clarify one thing, why this LP is a Banach algebra. Well, usually it's not, okay? So the only reason this is a Banach algebra is because we can, when this G is compact, okay? And my L1 space is going to be contained in the LP space. So we can just consider the convolution of two functions inside the LP space. So if I consider its P norm, so this is just the integral of the f of y, and you left translate your g by y, and then you do the dy. You treat this really as just an integral, this ly of g, you treat it as a function inside your LP space. So this one is going to be less than or equals to the integral of the f of y, the absolute value times the p norm of this translation, okay? But the translation doesn't really change the p norm, so you can move the p norm outside. So this is less than equals to the 1 norm of the f multiplied by the p norm of your g. Okay, so that's usually what will happen. So that doesn't make the LP space a Banach algebra. But the good thing about when G is compact is that you can normalize your Haar measure so that the integral, the mu of this G becomes 1. So you normalize it to be a probability measure. And because of that, that's the L1 norm will be less than equals to the really the P norm times the G P norm. So this one really follows from the mu G, the entire space is equal to 1. Okay, so some basic measure theory. All right, so from there, now your LP space is really a Banach space now. So the center now makes sense. Okay, if you convolute two things from the LP, you end up with something again inside the LP. All right, so now let's see why the center is precisely all the central functions. So if you consider what happens if you want to convolute f with g at x, okay? So this is just by definition, this is the integral of the f of, oops, what happened? Okay, so you have the integral of the f of xy, and then you have a g of the y inverse dy, okay? So that's on one hand. But on the other hand, you have the g convolute with f, okay? So they have to be the same. So this one is just equals to, let's write it another way. So let's write it as gy times the f of y inverse x, okay, dx. And so if you want to compare these two, okay, so the g is some arbitrary function in your LP space. So if you compare these two, well, you see you have a g of y inverse here, and you have a g of y over there. So you want to make the inverse, this y here to be an inverse, or so the one way to do that, well, I should say this is dy. One way to do that is when you want to swap your integral by changing y to y inverse, you need to pay a compensation for the modular function. But because your g is compact, the modular function is constant 1. Okay, so because g is compact, the modular function is always equal to 1. So this one, you can just swap to the g inverse, and you have a f of yx dy. Okay, so they are the same. Okay, so these two are the same. So now because your g is some arbitrary function, so g is anything inside your LP, and because your LP is a Banach algebra, so your f of xy and f of yx integrate with any g, they give you the same integral. So that just implies the f of xy is equal to f of yx for the f in the center. Okay, so in other words, f is inside ZLP of g. Okay. The other direction is kind of trivial. So if you have something inside ZLP of G, basically do the same thing. You can show it's also in the center. All right, so now we basically see that this explains where these the central function come from. They're essentially the center of these LP space as a Banach algebra. So now I just want to prove the proposition. So now we see that each of these characters they're in the LP, so they're certainly in the ZL2 of G, which is again it's going to be a Hilbert space because it has the inner product. I want to show that's going to be an orthonormal basis. Okay, so these chi pi is an orthonormal basis for the ZL2 of G. Okay, so they're now we know the span of these characters becomes a subspace of the L2 space. Right, so to prove that, so let's consider, first of all, let's consider the following. So by Peter-Weyl theorem, so you know that for every f inside ZL2 of G, what you can do is that you can write f as a summation of a bunch of trace. Okay, so we just show that formula from last time. So what you have is that you have d pi, and there are many ways of doing this. You can say that's the trace of the f hat of say f hat of pi multiplied by pi, and you can also say this is the f convolute with chi of pi. But anyways, that's just from Peter-Weyl theorem, and we just need to better understand what is exactly happening inside this trace, and moreover, let's first understand what is the f hat. Okay, So to see what is f hat, let's do some computation. So if I consider f hat pi with, and I multiply a pi x on the right, so f hat by definition is just equals to the integral of some fy. I have the pi of y inverse, and then I have the dy, and then I multiply the, so I have the pi x on the other side, okay? So what I can do is that I can move this inside, so it becomes the integral of fy. Pi is a unitary representation, so I have the y inverse x, I have the dy, and you now use the kind of the standard trick. You left translate your y by x, so you replace y by xy, and this one on the left you have f of xy, and on the right you have the xy, the entire thing inverse, so it becomes y inverse x inverse, so x inverse cancels out the x on the right, so you just end up with the pi of y inverse dy, okay? So that's what you have from the left translation. And now because your f is a central function, so you can just move the f to the y-axis with fy, the y-axis to the xy to the y-axis. So this is y-axis pi of the y inverse dy, okay? So basically now we do the same trick. You try to right translate your y by the x inverse. You multiply x inverse on the right hand side. The reason you can do the right translation is because you're, well, on the compact group, your left and right, your left hard measure is also right hard measure because your modular function is 1, okay? So let's do the right translation. So you have the f of y, so the x inverse get cancelled, and you have the y-x inverse entire thing inverse, which is pi of the xy inverse dy, okay? So that just, this is really just follows from your G is compact, and your modular function is constant 1. And from there, that's kind of easy now. So your fy is just a scalar, okay? That's a scalar inside C. So the pi x, you can move the pi x outside, okay? It really commutes outside. And you do the f of y, pi of y inverse dy. But this is just no other than the f hat of pi, okay? So what you see is that we end up with is we started with the f hat of pi, evaluate, multiply the pi x on the right, and it end up with pi x on the left times the f hat of pi. So your f hat is an intertwiner of your pi of x, okay? So the f hat of pi is inside C of pi. And because your pi is irreducible, but the Schur lemma tells you the C of pi, well, doesn't have too many things in there. It's just equals to some constant times pi, okay? So that's everything inside the intertwiner. So each of your f hat of pi is in fact a some scalar of the identity, okay? So let's call it C pi times the identity. All right, so now because it's C pi of the identity, so let's see what happens when you try to do the trace formula, okay? So if you want to do the trace of the f hat of pi, multiplied by this pi, so that's inside the repeater well theorem. All right, so the f hat now becomes a C pi times the identity. So this is just no other than the trace of the C pi scalar multiple of pi. Well, but the scalar multiple, you can pull it out. It becomes C pi times the trace of pi. So it just equals to C pi times the characteristic function of pi, okay? So your f, if you write it as a summation over all these irreducible representations of d pi times the trace of the f hat of pi times pi, now you can just rewrite this as d pi times c pi times the characteristic function at pi, okay? So that's a new formula. And so now I just need to tell you what exactly is d pi times c pi looks like. So what it does is, well, you can recall your f hat is a diagonal matrix with c pi, and it's a d pi by d pi matrix. So the d pi times c pi is just really the trace of the f hat of pi, okay? So that's just what it is. All right, and well, now let's just expand what is the f hat. Well, that's the trace of a convolution, so that's the integral of the fy. I have the pi of y inverse, or pi of y entire thing, the conjugate, complex conjugate. and you do the dy. And because the trace is linear again, so you can move it inside. And Fy is the scalar here, so it doesn't really affect the trace. You can move that out as well. So that's the integral of the Fy of the trace of the pi y, well, conjugate transpose of pi y star, okay? But when you take the star, well, you just transpose it and it takes the conjugate. It doesn't really change the diagonal other than putting a conjugate on the diagonal. So this trace is just really the characteristic function, but take the conjugate. Okay, so this is going to be equals to the characteristic function at y, and you take this conjugate. All right, so this one becomes this integral Fy with the chi pi conjugate, but you can treat it because they're L2 functions. You can treat them as the inner product of f with your characteristic function. So basically now we replace this by f with the characteristic function at pi. So what we have is that this formula here, so the f can be written as a summation of f inner product with this chi pi, all of these irreducible chi pi's, and you multiply by chi pi, and that formula just tells you chi pi is an orthonormal basis, okay? Only orthonormal basis can do such thing, okay? So that just implies the chi pi is an orthonormal basis for the z of L2 of G, okay? So that just finish this proof.